Okay, so it looks like we're going. So before we get into the math, quick announcement. So some of y'all may already know this, but at some point this, in about like 45 minutes or something, there's going to be some sort of a nationwide FEMA test of the emergency broadcast system. I think all our phones are going to explode in 45 minutes or something. So anyway, that's okay. It's right in the middle of the lecture. So be it, right? Anyway, I just wanted to make sure everybody knows so when it happens, we can just, if you need to look at your phone and press some buttons or whatever, go ahead, no problem. And I'm just going to kind of keep going with the lecture. Okay. All right. So here's what we were doing last time. We were talking about the implicit function theorem. And the big idea of the implicit function theorem is that if you have an equation given to you where one of the variables, let's say x sub I, is an input variable, right? It's just a variable in an equation, right? But you want to view it as being a function, then all you have to do is whichever variable you want to view as being a function, that's the variable that you need to take the partial with respect to. Specifically, you're going to be taking the partial of the function whose level set you're looking at, and if the answer is not 0, then yes, you can view that variable as being a function of the others, at least locally, which is typically all that we ever care about. Okay, all right, so that was the big idea, and we ended with this example. Notice that this fits perfectly, that there is a function here, one of whose level sets we're looking at, and we have been asked to decide if x is locally a function of the other variables. And so we arbitrate that by taking the partial derivative as described on the previous page and the theorem we just talked about, and you plug in the point in question, and it is not 0. And so the answer is yes, we can view it as a function. And that's where we ran out of time. Okay. All right, so the next natural big question. So it is a function, we presume. You've got a variable that you can now view as a function. What do we like to do with functions? We like to take derivatives of them, right? In particular, let's talk partial derivatives. So how do we do that? I'm going to show you two answers to that question. One is this very detailed discussion that I'm basically going to kind of wave my hands at. And if you want to see a more full and appropriate discussion of exactly how does this work, then this is a more full and appropriate discussion. What I'm going to do, what I'm going to talk you through, and what I'm going to encourage you to think in your mind is this much more compact and convenient point of view as I have represented here. Now, I am going to acknowledge first thing that my diagram that I've drawn here violates my own rules. And I know, right? And so mea culpa, I know this is a little math crime here. But the point is that this diagram, inappropriate though it is, there's the fix. You could totally fix it. This diagram, the fixed diagram, perfectly reasonable. Clearly a composition of functions. There's no issue to be worried about here. So again, you can check those details if you'd like. But again, day in and day out, this is the easiest one to work with. So let's ask the question, if f is given as a function of these variables, but if I want to view this one as being a function of the others, and in particular, viewing xi as being a function of the others, if I want to take the partial of xi with respect to xj, how would I go about computing that partial? Now let me change the way I've got this highlighting here. I want to compute what I'm going to casually represent on this diagram as that partial derivative. As I change xj, how much does xi change? Kind of the question I want to ask. So, the point of view I'm going to take on this is that as I change xj, kind of two things happen. On the one hand, as I change xj, that causes changes in xi, and changes in xi cause changes in f. There's that term. Right? constructed in a familiar manner to sort of the way we've been doing this kind of thing. And again, sloppiness in the diagram, and I know in victimless crime, it's actually totally okay in this case. And you'll recognize in this term, there's the partial derivative we're looking for, previously noted on the diagram is there, right? And then you'll notice further that that's multiplied by this partial derivative right there. So that's one of the two things that happens when you change xj. Here's the other thing that happens when you change xj, and this is the kind of the most immediately obvious thing. When you change xj, that makes an independent, direct contribution to how much f changes. So again, following our pattern, there's two different paths along which changes in xj can contribute to the overall total change in f. And now, of course, how much is f changing? What is this grand total change in f going to be? Well, it's a constant. It has to be a constant. It's not allowed to change. And so that total change has to be 0. Okay, so this is the picture that I have in my mind when I find myself wanting to compute one of these partials. And again, my goal is to compute this one, which we recognize as being that factor. And how do I solve for it? No problem. You just literally solve for it in the above equation. And in so doing, your formula is this. Everybody all right? See how that works? Yeah, question.
Well, regarding the diagram, when you're taking the partial of f to xi, isn't the arrow technically moving this way? Like you're going from f to x1 and then to, why are the arrows moving as they are?
So f is a function of all of the x variables, right? And this one particular xi of the x variables is a function of the others, and I'm interested in how when xj changes, how much that causes xi to change. I'm not sure if I answered your question.
Yeah, that works.
Is that good? Okay. All right, cool. Okay, again, if you want to see the cleaned up version, here's the cleaned up version. It's just that it's a little bit weirder and sort of more to worry about, but it's really just a straightening out of what I think is easier to think of this way. Now, I want to point out there is something about this resulting formula that we have here that seems pretty wrong, right? And that is this minus sign. And I claim that minus sign is very, very important, if only from a sort of a grading point of view. This minus sign is part of the right answer. Why is that minus sign there? Well, because, roughly speaking, if f is going to actually not change, then I need the amount that this path makes it change and the amount that this path makes it change. I need those to be opposites of each other. Right? So in the two different scenarios, in the two different paths that we consider here, they have to cancel, they have to be negatives of each other, and thus the minus sign. Now, let me talk about what happens, or what does it look like if you leave off the minus sign. So I'm going to just imagine that's not there. Oh, that's not, okay. Let's see, how am I going to do that? I guess I'd better go into pencil mode. Let me scratch that off of there. Okay. Suppose you just leave that off, right? And you say that this partial is equal to this thing because after all, can't you just say that the partial f and this partial f, can't you just say that those cancel? And can't you just say then that the denominator of the denominator becomes the numerator, which is in fact where it's supposed to be? It's very tempting, right? And of course, this is complete nonsense. This assumes that these two things are actually fractions. This assumes that these seeming numerator and denominator of these seeming fractions are actually well-defined things that mean the same thing everywhere in the equation, which they aren't and they don't. So this idea, the justification of why a student might think, I don't need that minus sign there, comes about from a fundamental misunderstanding of what these things mean and how this computation works. right? So one little minus sign, right? Teeny tiny little minus sign makes the difference between a student who looks like they completely don't understand what's going on versus a student who, if they get the minus sign correct, right, is just citing the correct formula. Right? And that's a huge difference. So now you got to keep in mind, a lot of people will look at a minus sign and think, minus sign, come on, minus signs aren't a big deal, right? We all make sign errors, happens to the best of us. You got to keep in mind there are different ways to make a sign error. One way to make a sign error is to just count wrong. I've done this a million times where I had 3 minus signs and somehow they canceled in my head, right? That's just a counting problem. Missing this minus sign is not a counting problem. This is a not knowing what is going on problem, right? So even though I know it looks like it's just a minus sign, you got to keep in mind it's a big deal minus sign. So again, as I wrote here, this is very important, and make extra sure that you remember that and that you get that right. Okay, let me show you an example. This is going to be a familiar looking example. You'll recognize this is the exact same equation we saw with the last example we looked at late Monday. Same surface, looking at the same point. And in that example that we looked at last time, we have already established that x is locally a function of y and z. You can find that example, of course, just on the previous page, right? We asked, is it locally a function of y and z? Why, yes, it is. Okay. So we're going to kind of go on and do the second half of the question now, after a fashion. And we're going to take our brand new function of y and z, and we're going to try to compute a derivative of it. How would I, for example, compute the z partial of our newly established function of y and z? Everybody on board with what the question's asking? Okay. So formula on the previous page tells us this. These partials are easy to compute, right? The z partial of this thing, no problem. Right. Then I have to, let's see here, I've got to take the x partial of this thing, no problem. A couple of partial derivatives. The big point, make extra sure you don't forget the minus sign. All right, make sure to put the minus sign in there and carry it on through. And then it's just a matter of computing, and in particular we're interested in what's going on at this particular point, so I plug in these values here, and our answer is that. Is everybody on board? All right, so that's how that goes down. Let's talk about how to remember this formula. There is something awkward about this formula and the setup of these kinds of questions in general. When you're talking about an implicit differentiation problem, it assumes that there are certain variables that are involved. Here, in this picture, the variables were called x1 through xn. In this example that I just did, that's not what the variables were called. They were called x, y, and z, right? And you could imagine you might be doing a problem in some other context. The variables might be p, q, and r, right? So don't try to memorize your way through that thing. The suggestion I'm going to make for how to remember the formula, really the best idea, is to understand how this picture gives rise to this equation and how you can then solve for the thing that you want. That's really the best way to do it, right? Is to understand the idea that leads to the result. Now, short of that, a arguably quicker and easier and just easier way to go about this. And I feel a little bit bad about this trick, but it's very convenient. First, write down your minus sign, because it is really important. You want to make sure you get that minus sign down there, right? Oh my gosh, I can't emphasize that enough, right? So minus sign first. And then just write down what we've already established is the naive wrong answer, right? So we know it's going to be a couple of partials of f. So whatever is in the denominator is the denominator of your numerator, and whatever is in the numerator is in the denominator of your denominator, right? And again, just pretend that they're fractions, which of course they're not, right? But if you put down your minus sign and then write down this classical mistake, the minus sign fixes the classical mistake. That's just how it works out every time. And in practice, day in and day out, as I do these, as they come up, that's actually how I remember this formula. So you'll notice that's what I did here, right? Step 1, minus sign. Step 2, denominator is the denominator of my numerator, and numerator is the denominator of my denominator. Yeah? Everybody good? All right, last thing I want to talk about, this is another really big deal, really important from a grading standpoint, exams kind of standpoint, and that is how will these questions be phrased, and how do what are your responsibilities as a student if you're giving a complete answer to the question that addresses all of the relevant, sort of needs. It is usually not the case that the question will come to you where it's given that x is already established, or whichever variable that you've been asked to take a partial of, it's already been established to be a function. Usually that's part of the question, right? So usually the question will look like this. It'll say, consider the surface, blah, blah, near a certain point, period. No free information about what is and isn't a function. And the question will then ask what is, and it'll ask you for a partial of, one of these variables with respect to one of the others. Now, frankly, that's kind of an inappropriate question. As stated, this question is asking for a derivative of something that we haven't even established is a function. It's sketchy. The reason that you see questions like this so often is because that's how life tends to work out. People come to you with inappropriate questions sometimes, right? And so what you have to recognize as the responsible party who's supposed to be giving a mathematically reasonable, responsible address to the posed circumstance, you're supposed to look at this and say, hey, wait a minute. We don't know. We have not yet established that x is a function. And so you're supposed to, one of your responsibilities is to realize that, the question has not even been established yet to be reasonable. We have to first go back and answer this question like we did here. This is step 1. All right. And then after having done step 1, that's the very first thing you do. Step 2 is to then compute the derivative as we did here. So make sure you're fully aware that this is the expectation, right? And not just in Math219. In any circumstance, you should always, if you've been asked to compute a derivative of something, you better make sure it's a function first. Right? That's number 1, and then go ahead and take the derivative after that by whatever method. So that's the point that I'm making right here. It is a very important part of the grading that you establish that you're actually looking at a function. Yeah.
If you find out that it's not a function, like it's not.
Oh, then it's a really bad question. Yeah. So if that happens, then let me think what to do about that. Assuming it's in my class that you're talking about, then you'd want to come talk to me and say, I really think that you've got a problem in the statement of your question here, right? And I will look at it again, and if so, then after my heart attack calms down, then I'll make an announcement to the class about how to treat that. But I'm usually very, very careful to make sure that won't happen. Yeah. Right. Yes.
So when we defined how to use the implicit differentiation theorem,
Yeah.
we used like a level set where it was equal to 0. Does the level set have to be equal to any
No.
certain constant, so long as it is a constant?
As long as it's a constant, that's all that matters. That's right. If this were C, that could come about, for example, by just adding, plus C over here, and the very first thing that happens to it is you're going to be taking a derivative of it, which is going to make that C go away. So yeah, it doesn't matter at all. Yeah, right. Okay, so that finishes chapter 2. We're going to move on now to chapter 3. Recall we've already done section 3.1. I did that in the middle of chapter 2 for sort of my pedagogical reasons. So now on to section 3.2 on arc length. This is kind of a weird section. Some of the material in this section is really, really, really important. Other of the material in this section is important for mathematical reasons that don't actually really quite affect y'all as much, and therefore don't really quite make the cut to be worth spending a lot of class time on. So I am going to give a bunch of time discussing this first part that's really, really important, that we're going to be using a lot throughout various different parts of the remaining part of the course. And then the rest of it I'm going to go through pretty quickly, and we don't need to sweat very much. Okay. So here we go, starting with the beginning. Suppose I want to compute the length of a parametric curve. Now, here's a parametric curve. Compute the overall length. You can probably imagine one of the first things I'm going to need to do is to figure out, okay, some little piece of that curve. Right? If I look at some teeny little piece of that parametric curve, and I'm just going to blow up that one little piece right here. Right? How would I kind of get my hands on that? What's the foot in the door that allows me to compute what that length is? Okay, so several things to say. First, I want to talk about this thing called the position differential. The dx vector. We call it dx, I'm going to say, for natural reasons. It's a differential. X gives me position. Dx means my linear estimate of how much that position changed. In other words, my linear estimate of the displacement. I was here. This is my linear estimate of where I am later. So dx, pretty natural. I think it's pretty immediately believable that displacement is velocity times time. Take your pick of either one of these notations. They both say velocity times time. Okay. Right. Everybody comfortable with that? All right. Now, next thing I want to talk about. Let's talk about ds. What is ds here? ds is distance. It's length along that little piece of curve. And the main thing we sort of need to observe about ds is that it is, if you sort of think about the semantics even of it, ds says how much distance, it's my linear estimate of distance traveled, and that should be closely related to my linear estimate of my displacement. And after all, what is the difference between distance and displacement? Well, a displacement is a distance in a certain direction, right? So ds should be, and is, the magnitude of the dx vector. Is that satisfying? All right. Okay. Yeah, so one other thing that I want to talk about here is this thing called capital T. This is the unit tangent vector, we call it. It's the unit vector pointing in the direction the curve is going, and it is very convenient, very important to use in certain circumstances. So again, I'm introducing it now. We're going to be using it a lot later. If you think about it, it's a unit vector that points in the direction of the displacement. The displacement is in the same direction as the velocity, and a unit vector in the direction of a given vector, like the velocity, vector divided by its own magnitude. Everybody buy it? All right, so now the last little piece of the puzzle that I'm going to talk about here before we go on is why can I rewrite dx, which we've previously observed, I can write like this or that. Why is it that I can also write it as t times ds? And I'm going to give you two different ways of thinking about this. How can I interpret t times ds? The first one is really just kind of a hand-wavy sort of intuition thing. Let's just think through what dx is. Dx has a direction and a magnitude. What direction does dx point? Well, it points in the direction of the unit tangent vector. What's the magnitude of dx? Well, it's ds. So when we write TDS, this is just our sort of classical way of representing the vector dx in terms of just direction and magnitude. T is the unit vector direction of it. ds is the magnitude of it. That's what a vector is. So I like that point of view. I think it's great for intuition. And I encourage everybody to kind of try to digest that idea. Here's the other point of view I'm going to give you, though. T, we have that formula. ds, we have that formula. And if I look at blue times green, right, this times that, notice the magnitude of v cancels, and you get what we're supposed to get. So specifically, here, let me write that down. When you multiply this times that, these magnitudes cancel, and you here. Let me clean this up. What you get is v dt, which is dx. Everybody happy? So if you want to take this kind of more formula algebraic point of view, this is a good way to do it. For intuition purposes, I really like this idea that TDS is just direction and magnitude of the dx vector. Yeah?
I'm still a little unclear about why ds is equal to the magnitude of dx.
So dx is a vector representing displacement. And let's just think intuitively now about what is a displacement. And a displacement says I'm going to go in a certain direction by a certain distance, right? So, yeah, go ahead.
But the thing that's kind of weirding me out is the fact that ds is curved, which means it's
Oh, yeah. So these are just linear estimates, right? So both ds and dx, they're both linear estimate. Dx is a linear estimate of displacement. Yeah, of course, you're absolutely right. It can't be the actual displacement because I don't know. The whole presumption when you're doing differentials is that we don't know exactly, or we can't be bothered, or something along those lines, to figure out the actual new value. Right? So dx is a linear estimate, ds is a linear estimate. When I wrote this as being the sort of curved part, I just needed to distinguish it from the dx vector. That's all. Yeah. Okay. All right. So moving along. Previously discussed, total length is a sum where we're adding up a bunch of these little lengths. Each one of those little lengths being, of course, magnitude of v times dt. And so here's our very convenient at this point formula for how to compute total arc length. Total arc length is an integral of speed. Keep in mind magnitude of velocity, sometimes called speed. Everybody happy? So the example I've got here is pretty boring. I give you a position function. In other words, a parametrized curve. Position is a function of time. And how do I compute the total length? Well, I'm going to compute the length with this formula right there. Right? I'm just going to take the velocity aka the derivative of position. I'm going to take that velocity, compute its magnitude. Keep in mind, magnitudes are square root of the sum of the squares of the coordinates. And boom, there's an integral that I would have to compute to actually get an answer to this question. And notice it's a pretty ugly integral. And this is not rare, sadly. This tends to work out this way. I mean, you can just see it right here in the formula. The formula for length is an integral of a magnitude. And a magnitude is a square root. And there's squares under that square root. And it's just very, very, very common for that to get ugly. So tragically, these integrals are often either hard to compute or impossible, unrealistic to compute. Okay. Everybody all right? Okay. All right. Next observation to make is called arc length parameterization. This is something where I'm going to go pretty quickly through this. It's just formulas ultimately. I want you to know where the formulas come from. I want you to have a vague sense for why we care about this. But this is just one of those things that I just wish we had more time for, and we just don't. So first, a reminder about parameterizations. Parameterizations are not unique. This curve right here, there's its graph parameterization. Very often, and I think in this case, the easiest parameterization. Right? Hope everybody remembers the graph parameterization. And now I'm going to pull a weird move here. I'm going to take that graph parameterization. I'm going to take the t, and I'm going to plug in this weird formula here. I'm going to plug in t equals q cubed plus q. Semi-random formula involving a brand new variable called q that I just made up. And when I do that, that turns into this formula, and I claim that this too is a perfectly valid parameterization for that same curve. Now you might think to yourself, how could that be? This can't be a parameterization of a quadratic. This one's cubic. Oh no, it's even worse. I see a sixth power in there. This doesn't look right. Right? But it is. Everything works fine. And you can even see exactly how it works fine because this formula for y, you can explicitly see how it is the square right there. Right? It is the square of x, namely that expression. And you can see it right here. That is the thing that's getting squared to make y. So it works. Everybody happy? Weird thing to want to do, I suppose, but that does give me an alternative parameterization of the exact same curve. Okay. So, nice little punchline, and now there are some little formalities that I don't want to have to worry about, but pretty much, formalities aside, annoying conditions aside, as long as you can take your parameter and write it as a function of some other parameter, plug it in, new parameterization. Okay, so here's the one that we're actually going to want to do. It's called the arc length parameterization. I'm going to point out that if I have some path here, so here's a path. Very often I like to think of a path as a road that we're driving along. I can talk about its parameterization with respect to time. And remember my road versus road trip metaphor. This parameterization is a road trip. This is the process of me driving along that road wherever I might be going, right? And at some point in time t, I'm at some particular location. And again, I can think of that location as being a function of time. But I could also think of that location as being a function of distance, right? I can think of that, whatever this distance is as being my parameter. You can actually see this on real roads. They're called mile markers, right? I don't know if y'all have ever noticed when you're driving along the road, about every mile or so, there's just a little sign, and it just says 284. And then like a mile later, 285. right? And they're literally just marking out distance from some, there's a 0 mile marker, some arbitrary standardized point, way some many miles back. So mile markers effectively are location as a function of distance. So the way we turn the one into the other is we algebraically relate those two parameters, kind of just like we did here. I just need to find a relationship between S and T. I need to know distance as a function of time. And we have a formula for how to compute distance. We have a formula for how to compute arc length, that is. And that formula for arc length is, you'll recognize from the previous page. It's just this right here. Don't worry about this tau business. The reason I have to use tau here instead of t is because t is already doing something, right? T is already the upper bound for the integral. I'm computing this arc length for a given fixed, right, known value of t. And as I compute that arc length for a given value, fixed value known of t, I need something to range between 0 and t. And it can't be t, right? Because t is the upper bound. So tau is just a placeholder. It's just a different dummy variable. It's nothing to worry about. Used to bug me when I was first learning this material. But that's really nothing to worry about. Okay. All right. And just like the previous example, when you have the relationship, when you can plug in what t is, just plug it in, and there's your new parameterization. So we're going to do the same thing here. Having found s as a function of t, you do have to invert the function. You have to solve for t as a function of s. So that's a little annoying, right? You have to solve for t in that equation. And having done that, you plug it in, and there's your position as a function of distance. Is that cool? Okay, it's nice for some, I'm going to say mathematical reasons. It is intrinsic to the curve. It's about the road, not the road trip, right? If you think about it, parametrizing with respect to time suggests that we're going to use me, my own experience, as I drive along the road to describe the road. The road was there long before I got there. The road will continue to be there long after I'm gone. Kind of weird to use my own individual experience there. Parametrizing with respect to arc length is natural. The mile markers, again, are that parameterization with respect to arc length. They were there before I got there. They will be there after I'm gone, right? So it's really ultimately very natural. And there's a couple other nice things. It's good for proving certain theorems. There it is. Okay. All right. Do what you got to do to your phones. Okay. Okay. All right. Oh, man. All right. Are we good? Okay. That was louder than I thought it was going to be. I didn't think it was going to be that loud. Successful test, right? The system works. Oh, my gosh. Okay. Certain nice mathematical reasons that we would want to do this that we don't need to worry about. Here's an example that I'm not going to go through all of because it's mostly algebra. I just want to point out, again, sort of kind of how it works. So if we have a parameterized curve here, and I want to reparameterize in terms of arc length, first thing I need to compute is the relationship between s and t. So I need to solve for s as a function of t, set up just exactly as we had above. And here's why these examples are awkward, is that when you go through and find your answer, even if the integral works out, which I had to go to some trouble to make an integral that actually will work out, we still end up with, in this case anyway, a pretty awkward relationship between s and t. And that's, I can't practically solve for t in this case. Right? So the examples that actually allow this to work out are very, very special. And arc length parameterizations tend to be more of useful in the abstract as opposed to useful in practice. Yeah.
Is there any reason why it looks kind of similar to the x1, like t minus 1/3, t to the third power, and t plus 1/3?
This is the little fast one that I pulled. This was a very carefully selected curve so that its velocity would look like this, which I chose very carefully so that when you look at the sum of the squares, kind of in some sense what happened is this minus sign turned into a plus sign. It is a kind of a nice little trick of algebra. This particular trick of algebra does come up surprisingly often in real circumstances. But this is all part of the careful crafting that I did with this example to make it so that this integral would be of a square root of a perfect square, so that the integral is even doable. And notice, even having chosen carefully so that this would work out, I still got kind of stymied here, right? So these are algebraically annoying examples. Okay. All right, so we're going to move on now to section 3.3. We're going to talk about vector fields. These are going to be, by the way, a major object of study for the last third or so of the course when we get into what we call vector calculus at the end. By the way, very, very important for engineering and physics, and I think really important for, I think chemistry majors should know more vector calculus than maybe they do, but for various different reasons. So a big deal. It's a completely new object that we haven't talked about before. So here we go. A vector field is a function of this sort. Specifically, the dimension of the input and the dimension of the output have to be the same. And specifically, when we think of such a function as being a vector field, the idea is that we take a particular point of view on it, namely that we view the inputs as being points, such as that point right there in 2 dimensions, or maybe this point right here in 3 dimensions. And then we think of what comes out as being a vector that we represent with an arrow with tail at the given point. So this is, this is the particulars of how we view such a function as this thing called a vector field. Inputs represent points. Outputs are thought of as vectors with their tail at that point, or in practice, in terms of the physical world, vectors that are somehow relevant to something that's physically happening at that point. And exactly what this vector field represents, well, it depends. There's lots of physical examples, so I'm not going to be specific about that just yet. Okay. All righty, so that's what a vector field is. Let's see some examples from a math point of view first. We'll start with this one here. And let's see here. There we go. So this vector field, you'll notice that the output is constant. Now, there is something about this picture that's unsatisfying. This right-hand side says it's a constant, but this picture makes it look like something's increasing. You know what I mean? One thing you have to keep in mind, this is not a graph. Right? Remember how I've got this soapbox that I'm always on, talking about how you got to make sure you distinguish the difference between a graph versus a level set. Totally different pictures. Geometric interpretations on these totally different pictures mean totally different things. Graph is not a level set, which is not the same, either one, as if you parameterize and are looking at the image of a function. And this is yet a fourth, totally different kind of a picture. So we're going to eventually have to figure out a calculus of vector fields, right? We already know some calculus of graphs, partial derivatives being slopes, stuff like that. We've talked about some calculus of level sets. Gradients are perpendicular to level sets, right? Stuff like that. We've talked about some calculus of parametric curves. The derivative vector is a tangent vector to the parametric curve. All different geometries because we're looking at different pictures. So what are we going to get when we start doing calculus of vector fields? And that's TBD. We're going to see our first examples of that on definitely not today. That'll be on Friday. Okay. Yeah.
Wait, so if that's not a graph, what is it?
It is a fourth kind of picture. I don't know that it has a specific name, but this is the kind of picture that we always use to represent vector fields. Yeah, and I could make up a name for it, but I'd be making it up. Yeah. All right. The main thing is, just make sure you don't conflate it with these other kinds of pictures. Right. Okay, so let's talk about how this is what this vector field looks like, and keep in mind the input, any point x comma y, such as any of these points right here, and see it says right here that the output 2, 1, and it's always the same vector, and thus we get all these arrows are same direction, same magnitude, always the same at every point. So this is what constant vector fields will always look like, something kind of like that, different vectors, different, different right-hand side will give a sort of a different picture. Is that cool? All right, let's see another example. Let's see here. Let's look at this example here. Now again, we have an input x comma y that we think of as a point. Fine. What am I going to do with this output? The output, you'll notice, also x comma y. That's the same x comma y that I have there, which I can think of as being a vector from the point of view of it being the position vector for that point. It's just that keep in mind, when you draw the field vector, you have to draw the field vector with its tail at the point where you've evaluated the vector field. So the punchline is then that, this specific vector field where f of xy is xy, the field vector will always point radially outward away from the origin with magnitude equal to the distance from the origin, and so you get a picture that looks kind of like this. Kind of weird. Everybody, Everybody all right? Yeah.
With the magnitude of the vector is the distance.
Yeah, that's right. This magnitude is, you might say it as, it's the same as the magnitude of the position vector because it's literally the position vector.
Yeah, x squared.
Yeah, that's right. Yeah. Right. Okay. All right. Here's another example. This one I'm going to leave some of the details for y'all as a good exercise, good little bit of mathematical weightlifting. Keep in mind, input x comma y means a point in the domain. The output, which, by the way, keep in mind, if that's a point, I can view it in terms of its position vector. And then let's see the output here, negative y comma x. I claim that it ends up looking like this, which I've drawn here now in the standard, the way you're supposed to when you're thinking of it as a vector field. But do keep in mind, this is a vector. Vectors don't actually have locations. And so I'm going to redraw, for my own selfish purposes here for the moment, same vector right there. And in order to understand the relationship between that point and that vector, I'm instead going to talk about what is the relationship between that purple position vector and this green field vector drawn in the wrong place. And here I think the relationship is pretty clear. This purple vector just gets rotated 90 degrees counterclockwise to turn into the field vector. And so this is what I want y'all to do for yourselves. Confirm for yourselves that the way you do this, the way you rotate a vector a quarter turn counterclockwise, If you think about it, it's a rotation. Rotations are linear transformations, which are represented by matrices that can be understood in terms of their columns, which are the images of the standard basis vectors. Y'all remember this whole spiel, right? This is one of the big facts of linear algebra that we use in this course, is that linear transformations are matrices whose columns are the images of the standard basis vectors. And if you do that for a quarter turn counterclockwise and multiply that matrix times xy, you will get negative yx. Fantastic little exercise to make sure you're good with the linear algebra. I need you to know, make sure that you can fill in those details. As always, if you get stuck, come talk to me, right? Office hours, after class, for example, right? Very convenient. And don't forget there's office hours for Professor Hughes, and we have a TA that has office hours on the weekends. You can ask any of us about that, yes.
Do you mind explaining why you have to draw two sets of arrows in this diagram and the one above it?
Oh, it's just for convenience. I mean, when we understand a vector field, it's always like this. There's a point that's the input, and then there's the output field vector that you draw with a tail at that same spot. But trying to understand relationships between those things, you're free to reinterpret those things in any fair, reasonable way. And it just happens to be, in this case, that it's easier to see the relationship viewing the input point as a position vector and viewing the output field vector as being another standard position vector. It's just for convenience. Okay, we're out of time. See y'all later. Have a good one, and see you on Friday. Let's see here. There we go.